So today is the day after we just took the trapezoids and kite quiz. I just put in the original quiz on parallelograms, proving if a shape could be a parallelogram, rectangles, and then the original quiz on rhombus and square. Today's quiz on kites and trapezoids also had a retake of the rhombus and squares. No idea how people did on that, but the grades were definitely not great on the original take. We haven't had a lot of time to practice it. Well, actually, that's not completely true. The quiz we took today, we had a lot of practice time last week, but the quizzes before that, we haven't really had a lot. So I said I would do a review video of everything. I'm just going to go over every quiz that's still available. Angles and polygons, parallelograms, proving and solving. Then I think we went to, well, rectangles was on one of those, and then rhombus, square. I'm not going to do trapezoids and kites yet since I just gave you guys the quiz today. All right, so to start out with, here's something that might help you. It's a lot of information, but for those of you that struggle in math but do well in other classes, this might be something you want to use. It's got every shape pretty much that we've done. It doesn't cover how to handle angles and polygons when they're, different numbers of sides, but it does kind of have the features of the specific different shapes like square, rectangle, parallelogram, rhombus, kite. That's I don't know if it's called an irregular trapezoid. Actually, they call it trapezoid. Zodium or trapezoid. I'm going to zoom in a second. We'll see. And then isosceles trapezoid. And then just an irregular polygon, I guess. So here's a closer view. You can try to take a picture of that if you want. Or if you just want to see it up close or closer, I guess I can probably zoom in one more time and it'll still fit on the screen. Yeah, there we go. All right. Well, let me zoom over. Whoop, or not. What in the world? Let's try that. There we go. All right, so again, these are all quadrilaterals, which is what the entire chapter was about, except for really lesson number 1. So there you see the features of, so you can take multiple pictures, whatever you want to do, record with your phone. So that's all the properties for, it calls it a trapezium. I'm not sure why it called it that. It's a trapezoid. This shape right here is a trapezoid. It's got 4 sides. Again, trapezoid. We'll go over what that isosceles part means in a second. So there's some stuff you can memorize. Don't worry about this last thing right here that has symmetry. We didn't do anything with symmetry. We just want to know the other properties. So diagonals, angles, sides. All right, so with that in mind, I'm just going to go from the very beginning all the way through the square, I guess, is where I stop. I'm not going to do trapezoids and rhombus yet. All right, so first thing we started out with, let's see if this works. Oh, no, that's not. So we just started out with what we call a polygon. That could be any shape that has closed sides, any number of sides. So that's 5. I could just keep going forever and ever and ever and ever and ever and ever. That has 6. No specific properties of those. We can't say that triangle is a right triangle. We don't know that that has a right angle in it, even though it kind of looks like it. About the only thing we could do with these shapes, we said, is to calculate out the sum of the internal angles. The way we said we could do that, or the principle we used, is if we drew a line from one vertex out to all of the other vertices, then we could create triangles. And we know from past lessons, every triangle is 180 degrees. So we would have, in a 4-sided figure, 360 degrees. And again, this is the angles and polygon chapter. Now, if we took that and we did it here, we could draw one there. Oh, I didn't mean for that to be such a fat line, but that's fine. So now we have those three lines, and we could say, all right, well, drawing in those three lines again creates multiple triangles. 1, 2, 3, 4 triangles. And again, we know every triangle has 180 degrees. So a shape that has, what is that? 1, 2, 3, 4, 5, 6 sides would have 4 times 180 or 720 degrees in all of the internal angles. I think a lot of people are confused about what internal angles are, and I'm not going to spend a bunch of time on that. But an angle is just the measure at a corner, measure at a vertex. So I'm going to get rid of a bunch of that stuff real quick. This is the measure of one angle. That's the measure of another. And these are all different. I'm not going to worry about putting different marks, but all of these angles have measures. If we measured each angle with a protractor and then we added them all up, if we could do that absolutely perfectly, they would total 720 degrees. And then for, a triangle, we know it's 180. So if we measured all the angles of a four-sided figure, it would be 360, and then a five-sided figure. And we said we could just create a chart if we really wanted to. And every time we add a side, starting with 180 degrees for a triangle, we're really just adding 180 degrees. So 4 sides had 360, 5 sides had 540. Now, the other way to do it, we said, was with a formula. We said, based on our experience with this and just drawing triangles and other things, what we were really doing is just subtracting 2 from the number of sides and then multiplying by 180 to get the total internal degrees. So all these numbers that I circled. So that formula worked on all of the numbers, or all of the, measures of the interior angles. Now, the next step was we went to a regular polygon. Kind of the same concept as far as figuring out the interior angles. But what we knew about a regular polygon, just the definition of a regular polygon, all of the sides are the same measure and all of the angles are the same measure as well. I'm sorry, all of the sides are the same length. So we said, well, wait a minute. If we know all of the angles have to be the same measure, and we know a triangle has to have 180 degrees, then that means every angle has to be 60, 60, and 60. And then we did that for every shape. That has to be 360. Well, then that's 90, 90, 90, and 90. And then we did that. So basically, we were just taking the total and we were dividing it by the number of sides every time. So 540 divided by 5. Some people messed up and they divided by the number of sides, subtract 2. You don't do that. You want to include all of the angles. So you need to divide by however many angles there are. So 540 divided by 5, every angle was 108 degrees. So if we added one more side, that would be 720. And then we would divide that by 6 by the entire number. So that would be 125, I believe. Is that right? Oh wait, I wrote the wrong number. That's why I'm getting the wrong answer. Hold that phone. So this is 720 in this. So 6 goes into that once, twice. So yeah, 120 degrees for each individual angle. Again, this 120 is each individual angle. They're all the same measure. So if they have to total 720, then they all have to individually be 120. Now, if we had a big number of sides, like 30 or 40 or 50, we said we would probably have to use this formula right here to calculate out the total interior angles. We wouldn't want to try to draw the figure and draw triangles in. We'd have to use the formula, and then we would just have to make sure we divided by the total number of sides, not in subtract 2. Do not divide by that. Divide by the total number of sides, because that's also the total number of angles, and we want to make sure we're figuring out the measure of all the angles. which would be, the same number for every angle. All right, so next we went into a parallelogram, and we learned a bunch of principles of parallelograms. They were on that past diagram, that little chart I showed. I'm going to quickly go over them. We said opposite angles are congruent. I think there were 6 theorems we learned. So that's theorem 1, opposite angles congruent. So I'm not gonna write all these down. You can write them down. We said opposite sides are also congruent. That was another theorem. I don't believe it was a theorem. The definition of a parallelogram is that opposite sides are parallel. So you need to know that. That is not a theorem, but it is the definition. So if you see a figure and opposite sides are parallel, that would also tell you that it's a parallelogram. Again, just so you remember, the way we show parallel in a figure is something like this. Arrows, and the arrows can look different ways. They can be colored in or not colored in. And then I would have to, actually here, let me do this. So we'll put 2 more here. And then we'll put only 1 on this one down here. I'm going to make just arrows like that. Just don't have enough room. So again, that's a definition of parallelogram. I'm going to get rid of some of this. You can go back and look at it again if you need to. So again, opposite angles congruent, opposite sides congruent. We said the consecutive angles have to add up to 180. That was a theorem as well. Now, that does not prove that it's a parallelogram. This is when we know it's a parallelogram, we can say consecutive sides are congruent. There's a difference between being able to prove something is a parallelogram based on information versus being told it's a parallelogram and then knowing what is true about the figure. Again, the theorems are in the book. You just need to study and figure out which ones you need to know for which situation. So let's see. Another theorem was if we take one diagonal and draw that in, not mean to really use the big fat one again, but that's fine. If we take that and draw it in, that creates, even though it's not drawn in perfectly, that's fine. That would create 2 congruent triangles. So we went through and proved it out. I'm not going to worry about it, but basically we were able to use, and this is I keep forgetting to say this in class. If you really have a good grasp, I mean, go back and look at proving triangles congruent, because that would really come in handy in a lot of these lessons we're going to be doing. Those 4 things, if you can ever prove those 4 things in some of these shapes we're seeing, you can figure out which triangles are congruent. And by figuring out which triangles are congruent, you can figure out which line segments are congruent. So even before we know, well, as long as we know that's parallel lines, which you would have to at least know that we have parallel lines, you can basically use, and then the other lesson that we said was handy is the 2 lines in a transversal thing. Between congruent triangles and 2 parallel lines and a transversal, we could prove all of this stuff through congruent triangles and congruent angles. All right, so if we draw in the diagonal, then we create 2 congruent triangles. Again, we kind of already know this, but that's congruent to that. That's congruent to that. The middle line is congruent to itself because it's shared. So side, side, side. We could have also used some angles because we know because of the parallel lines, a whole bunch of angles are congruent. If you're not following all of this, don't worry too much about it, but you just have to memorize the theorems. All right, so next there was the proving a parallelogram. A lot of people missed a couple of them. One was not a theorem, it was the definition. So we said if we know a few things are true, like opposite sides are congruent, that's a theorem. Has to be a parallelogram. No other way to have that happen. without the lines being parallel on the top and bottom, left and right. We also said if the angles are congruent, opposite angles, then that had to be a parallelogram. No other way that could happen. Even if we don't know the sides are congruent, there's no other way that can happen without it being a parallelogram. We said, believe this is, I mean, there were other ones that weren't theorems, I think, but just trying to remember the theorems. If we have a side that is both parallel and congruent, that is enough. There's only one way that can happen, and that's if that is a parallelogram. The top and bottom would have to be congruent in order to make a polygon if the left and right side were both congruent and parallel. Again, that's a theorem. And it could have been the top and bottom sides that were congruent and parallel. Doesn't matter, same thing, because you can always rotate a figure, remember? So the one that a lot of people miss was just the definition. If you see this, if you see that, that's actually not the definition, but it is true. There's no other way to connect those two parallel lines. The distance between these endpoints would have to be the same. And you could do this with congruent triangles. Actually, let me get rid of that. The only way that you can have those two blue points connected and the two red points connected would be if it was the same line, if you have two parallel lines on the left and right. So that isn't a theorem. I don't believe it's even really technically the definition, except for the fact you can prove it, that the top and bottom would have to be parallel in order to do that. So that technically was one you had to get correct, even though it wasn't a theorem. That was more of the geometric reasoning part. I didn't take off tons of points, but you couldn't get a 100 if you missed it. And a lot of people got it right. So anyway, that was the definition and theorems about a parallelogram. You then needed to use that to do math. I'm not really going to do a bunch of problems in this, but you know, if I told you this angle was some measure and this angle was some measure, again, look for the degree symbol. I still have a bunch of people trying to make this 3x subtract 8, which doesn't have a degree symbol, and then somehow adding that to something else that doesn't have a degree symbol. I shouldn't have said 3x, but we'll just say that. And then saying that equals 180. 180 is degrees. We would never use that as a, well, I shouldn't say never, but I doubt highly you're going to see a length of 180. 180 is going to be degrees. 360 is degrees. Normally 90 is going to be degrees. If you don't see the degree symbol, don't use those numbers. You got to figure out another way to do it. Typically, there'll be some other expression that you would have to use or some number somewhere that they would give you. But yeah, don't use 180 unless it's about degrees. So in this case, these two angles would be about degrees, and that's when we could use the 180. Again, they might, say this is, they might just give you numbers, but they might say 5x subtract 12. And then over here, they might say 3x plus 80, just making stuff up. And then now, if you know those are about degrees, then you can say, okay, well, that's about the angles. I know those two angles are consecutive. They're not opposite vertices, not opposite corners. They're, on the same side, which means they would have to add up to 180. But you can't take sides and add them up to 180, which a bunch of people are still doing. See what else on. So there's a bunch of stuff on parallelograms. I'm not going to go through and solve everything, but if they do tell you something about sides, oh, I forgot one of the. Yeah, let's go back to that. So also for the theorems, we said we take the diagonals of a parallelogram. They bisect each other. If I take that diagonal, oh, both diagonals, perfect. So if I take the diagonals of a parallelogram, they bisect each other. Now, if you're not sure if a shape is a parallelogram, like if they're asking you, can you prove that this is a parallelogram? The diagonals bisecting each other does also prove that it's a parallelogram. So that does prove it's a parallelogram. So it kind of goes both ways on that, kind of like some of the other things. So when you have a parallelogram, the diagonals bisect each other. That is true for everything. Like all of these things about a parallelogram are true until you get to a kite. That was really the first thing we did that wasn't a parallelogram. Trapezoids and kites are not parallelograms. Everything else we did, this is true. Everything I just went over is true. So next, after parallelogram, we moved into rectangle. So again, a rectangle is still a parallelogram. It is just a specific type and has its own properties. Let's draw those. Hopefully I can do this relatively well. Yeah. So a rectangle, again, it has everything I just went over. It is a parallelogram. So all that other stuff is true. It just has some other specific things. One of them being all of the angle. Oh, one of the theorems was also if one angle of a parallelogram is 90 degrees, they are all 90 degrees. Again, if opposite angles have to be congruent, that means the other angle across from it is 90. And remember, consecutive angles have to add up to 180. So the angle next to it has to be 90. So that it is a theorem, but it's kind of a pretty simple one to figure out. So in a rectangle, all angles are 90 degrees. That's one thing that's different from other parallelograms. And then the other thing that is different is that the diagonals, not only do they bisect each other, but the diagonals themselves are congruent. Those two yellow lines, the thicker yellow lines I just drew in that rectangle, are the same length. So we said, well, wait a minute. If we're starting with the same length for the diagonals, and then we're bisecting, right? Diagonals are bisectors. That's what I wrote right up above, right there. So if I'm bisecting two things that start as the same length, we said really what happens is these are just all the same length. Because if they're both, let's say 20 to start, and I divide them both in half, then I got 10, 10, 10, and 10. If they're both 10 to start, the diagonals are both 10, and I divide them all in, or both in half, then I got 5, 5, 5, and 5. So if I'm starting with the same length for the diagonals and I bisect them, then I'm always going to get the same length. So we said if that's the case, actually this is always the case. Remember, don't forget the point in the middle is a midpoint whenever we're dealing with parallelograms. So that point is a midpoint. I think that was everything. Boy, we really struggled on rectangles though. What is not true about rectangles is where these angles are 90, those smaller angles, like where I'm splitting the 90 degrees up, those smaller angles are not congruent. Like they're not 45 and 45. One of them is much smaller than the other one. I'm going to get rid of all of that and kind of show you this again. So these angles here, I hope you can kind of see it. That angle is not congruent to that angle. Now they're part of this angle, so that they would have to add up to 90, but, and remember, this is a property of a parallelogram. We have two congruent triangles here, and we can prove that out if we really wanted to, but this is a congruent triangle with this triangle here. So there are congruent angles, it's just not the ones that are right next to each other. This one over here would be congruent to this one. And again, this goes back to parallel lines and a transversal, and those two would be congruent. So if I have two lines and a transversal, we said that's congruent to that. So it was alternate interior, if you remember that. The ones right next to each other. The ones next to each other would have to add up to 90 though, because they, they make up this corner right here. And that corner is 90 degrees. That was really the only new thing about rectangle, was that the diagonals are congruent, which means all of these smaller segments are congruent. So next, after rectangles, we went on to rhombus and square, which is the last thing I'm going to do. So we said a rhombus, and I drew this out for you, is really just a square. Oh, that was horrible. Let's try that again. I shouldn't have picked my pencil. Piano. Oh, there we go. So let's try that again. Pretty close. We'll say those. So again, if I created it from a square without changing the length of any of the sides, then all of the sides were congruent, we said. So that was kind of the definition, not really anything, like not a theorem. The theorems were both about the diagonals. It said if I draw in diagonals, first of all, the diagonals are at right angles. So that means I have 4 right angles in the middle. If one of those is a right angle, they're all right angles, because of vertical angles and collinear pairs, meaning, angles next to each other on the same line have to add up to 180. So that was one thing. The diagonals bisect each, I'm sorry, the diagonals are perpendicular. The other thing, even though it doesn't look like it, is that the diagonals also bisect the angles. So those 2 angles were congruent, the 2 little angles right here, where we split the big angle. Those are congruent, those are congruent. So basically all 4 of those are congruent, because the opposite angles are congruent to start with. Then that would mean, well, in this angle right here, which I'm talking about the big angle, those 2 opposite angles are congruent because it's a parallelogram. Well, that means these are congruent right here, and these are congruent right here. And the 4 internal angles, because it has 4 sides, interior angles, would have to add up to 360, which is the way you do some of the rhombus problems, understanding that the total of all the interior angles is 360, but understanding also that when you have diagonals drawn in, you're basically bisecting every angle. And then for a square, you needed to understand for a square, pretty close to a square. A square has all of the properties of a rectangle. Well, first of all, it's got all the properties of a parallelogram. So go back to the beginning of the lesson or the video. But it's got all the properties of a rectangle, which were that the diagonals are congruent. And then it's got the properties of a rhombus, which says the diagonals are at a right angle, and that it bisects all of the angles. The diagonals bisect all of the angles. So those are bisected, and those are bisected. I don't know why it's not making a curved line. So a rectangle has all 3 of those things, in addition to all of the properties of a parallelogram. And then that allowed you to do the math in the problem on a square. That's all I'm going to do for now. I have no idea how people did on the trapezoid and kite video yet, but the most commonly missed things were just not understanding those theorems. So I'm not going to do a bunch of problems. You have problems assigned in the book pages. Go back if you don't remember what they are. Show your no, that's not. I think that's trapezoid stuff. That's actually trapezoid stuff. So was that, I think. Yeah, kites still. Trapezoids. So that's still trapezoid here. Let me just go back to the very big lesson. So there's the problem there that we did. You can go back to that video if you really want to. It was just basically saying, okay, this equals that. It's a parallelogram, then those are congruent. Well, if it's a parallelogram, those are congruent. If you are saying two opposite sides, or I'm sorry, two opposite angles are equal, because in this case it has a degree symbol, so it's about the angles. If you're saying the angles are equal, then you just set the angles equal. Circle what's in the angle and set it equal to what's in the other angle. You can say it in words, you should be able to create a formula. So we just set that and then we solve for y. Same way with x. F7x equals 56. I'm not going to go through a bunch of these. You can go back and watch the old videos, a bunch of problems. Oh, let's see. Oh, that was definitely, this is like proving something is a parallelogram. That was not enough information, so that was a no. I think there were only two no's. Well, I think 6 was a no, actually. So maybe I told you wrong. Maybe that's not the one on the quiz, but I don't really know. Oh, I'm sorry. Yeah, that's a no. So what I told you was wrong earlier. Totally wrong. Because it doesn't say these are the same length here. So yeah, you could have this one, this bottom line here, if they're not the same length down here, then yeah, I was thinking they were the same length, but they're not. So yeah, scratch what I said earlier. Yeah, if you have this one in number 6, that is a no. It's a no in number 6. So yeah, just those two were no's. All of the other ones were yes. Oh, so then problems. Oh, so yeah, there were problems just like that on the quiz. Yeah, so there were problems just like this on the quiz, I'm pretty sure. This was on the solving parallelograms quiz. Which I did change a little bit, so make sure that actually I changed the angles in polygons and the solving parallelograms. I don't think I've made any changes to the rectangles, rhombus, all that stuff yet. Square. Well, square. There weren't really a ton of problems with rectangles in the book, so you can go back and look at. Oh, don't forget about this. Yeah, this was on there, and a lot of people aren't sure if to do. If I know sides of actually almost, I shouldn't say nobody, certainly less than half of people knew what it means. If I know the sides of a right triangle, because that is a right triangle. This one right here. I'll outline it in blue. So this is a right triangle right here. If that's a right triangle and I know 2 of the 3 sides, then I can solve for BC. So solving for BC is that a squared, b squared, c squared thing. It's not, scratch that. Squared, squared. A squared plus b squared equals c squared. Well, if I know what BC is, then I know this is the midpoint. So I know what those two are. I have to split BC in half. Well, then I could say, well, wait a minute. We just said for a rectangle, if BC would equal AD, because that's one of the principles of a rectangle is that the diagonals are congruent. So if I know that BC equals AD, then that means whatever I get for BC, AD would be the same length. Well, if I just want this one segment right here, if I just want AE, well, I would just split the number in half that is whatever BC comes out to be once I do a squared, b squared, c squared, because AD and BC are the same. So AE is 1/2 Ah, right with a highlight. So AE is 1/2 of, and of means times, whatever AD is, and AD is whatever BC is. They're the same. Remember, that's the property of a rectangle. Diagonals are the same. All right, so here, let me just go back one time because, yeah, I was having a brain cloud and show you the rectangle thing that I probably confused you with. So again, in rectangles, I'm sorry, in parallelograms, come on. So in parallelograms, in order to prove it's congruent, if this is not enough information, if I just know those are parallel and that those are congruent, that's not enough because I could always I'm gonna have to I can't visually see why that doesn't work. True. Because if the two on the left and right have to be congruent, if I angle one out, I can't lengthen it, but I can't lower the top. I'll have to figure that one out because to me, I can't visualize any other way that doesn't. It's not a theorem for sure. So I won't worry too much about that one on the retakes then. And I'll go back and look at the other quiz too and see if there were a lot of people that, I don't even know if I marked it wrong on that quiz when I graded. I'm just thinking about it right now without looking at the book. Anyway, so it's not a theorem, but I can't see how it could possibly not prove that it's a parallelogram. So I'll figure that part out.